this work? Okay. Hello everyone, welcome and thank you for coming to this third Kaiser Spring lecture. Today's lecture will be given by Dr. Ana Heras, a Spanish astrophysicist and the lead project scientist on the mission she will be discussing today, namely the ESA PLATO mission. This mission will search for planets similar to our Earth, orbiting stars like our Sun. And moreover, she's also working at ESA here in North Bank. PLATO is set to launch in January 2027, is being currently developed, and it will be so sensitive that it will be able to find planets like our Earth at distances from their host stars, which will allow the conditions for liquid water to exist on the surface, which also makes it very interesting in the search for habitable planets. For today's talk, she will talk about how the PLATO mission will work, what the techniques will be to discover the exoplanets, what properties of the exoplanets it will be able to discover, and how this will help us with our understanding of not only other planets, but also our own Earth. So thank you again for coming, and I hope you enjoy the lecture.
Yeah, thank you so much for this nice introduction. And I also want to thank the Kaiser Spring Lecture Committee for inviting me. Thank you very much, and of course all of you for coming. So, okay, I will try to share the best I can the work that we are doing. Actually, I'm here talking about the work that hundreds of people are doing in Europe, in many European countries, also in some non-European countries. So, yeah, please keep in mind that this is the effort of a large number of scientists and engineers in many institutes and companies. Okay, so, well, let's take a look at the sky as our famous, beautiful Gaia satellite has seen. So this is just a view of the galaxy. You see here, well, a large number of stars, many more than what you normally, of course, look by naked eye. And from what we have known until now, and we have detected with all the observatories and with the space missions, then we know that there are at least as many planets as stars in the galaxy. So just try to imagine, and we are talking about more than 100 billion stars in the galaxy, and then we know statistically, we haven't seen it, we know statistically that there are at least as many planets as stars. And how do we know that? Well, there are a number of observatories and missions that have been really productive and well, telling us everything that we know so far, starting with the ground-based observatories. So the ground-based observatories were the first place with an exoplanet was discovered around a Sun-like star. And for this discovery, Michel Mayor and Didier Queloz got the Nobel Prize, and it was on an exoplanet that was much larger than the Earth, much closer to its star, which was called 51P, because we put letters now to specify also the exoplanet, and it was discovered in a ground-based observatory. And after that, there were a number of missions that were dedicated to discover and study exoplanets. So, for example, we have here the Corot mission. Actually, the Corot mission was a French ESA European mission, which was the first one dedicated to the discovery of exoplanets. And they found the first terrestrial planet that we can characterize it like this. Also, it was very, very close to the star, so it was very hot, but it was again a European mission who made this discovery. So just keep it in mind that indeed Europe has been a driving force in the field of exoplanets until now. Then we have two NASA missions, Kepler and TESS, which were the next ones that have hidden the largest number of exoplanets that we know so far. And I will be talking about the method that they've been using for that. And then we have the Cheops satellite, that is an ESA mission that is looking at exoplanets that we know already, but when we want to know much better their characteristics, then we observe with Cheops. All these, I'm just going to see if this works. Yeah, so then this works well. Okay, so then these missions that are here, they are not dedicated to exoplanets alone, they are multi-purpose observatories, but they also been contributing to the analysis of exoplanets in terms of, for example, characterization of their atmospheres, or Gaia, like what we will see in the end of this year, in the discovery of new exoplanets with other methods. But for the Gaia mission, we still don't have so far A lot of results, but they will come very soon, so just keep it in mind. Okay, so the fundamental questions that we want to answer when do we see these stars and then we imagine the exoplanets around them, or we, in some cases, detect them, is that how do planetary systems form and evolve? And then when I say planetary systems, I also say our own solar system. When I was a student, we didn't know anything about other solar systems or stellar systems, so we only had one, and all the formation theories that we had were based on one case, which was indeed the one that we are living in. But then, since we have discovered so many other stellar systems with completely different configurations, we really need to understand much better how all these systems evolve to understand also better how our ones form and evolve. Because then, yeah, we have found that the assumptions that we made to solve one case, they don't apply to others. So then it means that we have to adapt our theories and we have to learn more. We also want to know, is our solar system special? As we said, is it really exceptional? Or are there other systems that are like ours? This is obviously a question, a profound question that we always ask ourselves. What makes a planet habitable? Well, habitability, I think that, I don't know if you had already a lot of details on astrobiology in other lectures, but it's a very complex question, very complex. So it's not only that today I will talk about water on the surface of a planet, but this doesn't guarantee that there's going to be life. It's just that has facilities, or there is an environment, but actually habitability is a very complex issue that has many different elements that one has to take into account, but we have to start somewhere. And then the first place to start is to know many more planets that are maybe similar to ours and see how they are. And again, I mean, is the Earth unique, or has life also developed elsewhere, which is connected also to the previous question. Well, why do we know much more? I mean, we know, indeed, we have observed billions of stars. You know, we can also observe galaxies now with JWST that, they are very close to the beginning of the start of the universe. So, yeah, why are know so little about exoplanets, and indeed, why we have started so late? And the main reason is because exoplanets are very difficult to observe. It's not simple. I mean, we really need very accurate instruments, and we are really developing techniques that 30 years ago were almost unthinkable. And I hope that in 20 years we'll also see things that we consider now that they are very difficult to do. Okay, so then the main question is that when you observe an exoplanet, so the star that is beside it, of course they are in the distance, they are very close, so this is one of the first things that one has to take into account, and the light of the star is, or the brightness of the star is 1 billion times, 1 billion brighter than the exoplanet. And then if you go in on reflected light, this is 10 billion times, and only when you go into the infrared, so then it can be a little bit, 10 times or 100 times less the difference between both. But you can imagine that we are talking indeed about huge difference between the brightness of the star and the exoplanet that is beside it, in the distance really close to the star. So well, this is just a bright star, so of course the brightness is distributed all over the other detectors. That's why you see these halos around. And basically we have to use techniques that in the future will block the light of star. And then we have it already now for some stars that are a little bit younger, and the exoplanets are farther. But when we want to observe Earth-like planets around Sun-like stars, we want to block this star, and then indeed, only by blocking the light with very difficult techniques, we can see the planets that are around. But okay, I will not be talking about this today, because Plato is using another technique that I will go through now. Okay, so Plato, in the same way as Tess and the same way as Kepler, is using the transit method. And conceptually, the transit method is relatively simple. So then you have a star, and then when the planet goes in front of the star, basically blocks the light. So then conceptually this is relatively simple. So we have an exoplanet, it goes in front of the star and it blocks the light, and we see a decrease in the brightness of the star. And actually this decrease in the brightness of the star, now indeed we can measure. I mean, since in the last 20 years we learned how to measure it, and it provides us with a lot of information also on the planetary orbit. It tells us indeed what is the distance from the exoplanet to the star. It tells us what is the planet radius with respect to the stellar radius, because of course if the exoplanet is bigger, what you will see here is that the light is more blocked. This is logical. And if the planet is smaller, so then this will be smaller. And then it also gives us an idea of the orbital inclination, because it depends, I will explain afterwards, what the inclination of the orbit is, then you can determine if there's a transit or not. If these transit times vary, so then sometimes it's a little bit earlier or sometimes it's a little bit later. You can also derive the planet mass, because normally it means that there's also an influence of the exoplanet with other exoplanets that are around, and then you can make a calculation of the respective masses and you can determine the mass. But this only happens in less than 10% of the cases. So that's why normally we don't assume that we are going to determine the mass with transit ratios by default. And also very importantly, spectroscopy. So by doing this, but instead of observing only in one color, to do it with several colors, then we can determine the composition of the atmospheres of exoplanets. And then this is the technique, for example, that JWST is using in many cases. But we are not doing this with Plato. Plato is not doing a spectroscopy, we are not analyzing atmosphere composition, but the transit method, as I said, has been very successful. This is the method that has given us the highest number of exoplanets that we know so far. Okay, so as I said, here you have the decrease of the light of the star when the exoplanet goes in the front. And then, well, this is, I put a formula, but I think that it still is good to give an idea of relative simplicity. There are more terms here, but the main one, and then indeed the one that dominates, is indeed the decrease of the flux is proportional to the ratio of the planet with respect to the star to the square. So actually you see it's a direct relation here, so you can derive this. And when you have a star like the Sun, and then you see a planet like Jupiter passing in front of it, then the decrease of the light is 1 in 100. If you have an exoplanet like the Earth, the decrease is 80 parts per million. So it's less than 1 in 10,000. And then you have to detect even with better precision, because you want to have several depths too, because here you have noise, so then indeed, in order to detect it properly, you don't want to do better than that. So therefore, you can imagine now what we are talking about seeing the light of a star and being able to see variations in parts per million of this variation. And also stars vary because they are not all the time quiet, or sun varies a lot. This is the measurement that we want to make. Okay, the issue with the transit method is that the probability of transit is relatively small, especially when you want to observe an exoplanet that is at the same distance of its star as the Sun, as the Earth from the Sun. So here you have a scheme, so here you have the star, here you have the planet, and the only way that an observer can see this transit is if the plane of the orbit is in a certain angle with respect to the observer. Because if you have the planet, for example, that is doing like this, so then it's doing, here is the star, maybe it's better even with the hands, no? So here you have the star, and then if the exoplanet is doing like this, you will never see the transit clearly. So you only see the transit when it's orbiting in this, and then at this angle, when the distance is to an astronomical unit, or the distance to the Sun from the Earth, this is between 1 in 100 and 1 in 200, the probability. Which means that you need to observe, even if the planet is there, you need to observe between 100 and 200 stars in order to see a transit, even if because maybe the orbit is in an angle that is not convenient for the transit. So this is also very important to understand our mission. So the transit precision Indeed, the transit probability is relatively small, so we need to observe many stars if we want to discover new exoplanets. Okay, another method. So then this is the second most successful method in terms of numbers. And this is actually the method used for the discovery of the first exoplanet that gave the Nobel Prize. In this method, in the same one as the transit method, we don't observe the planet directly. Because, as I said, the only way to do it is to blow by blocking the light of the star. So what we are looking is at the star. So then we here have a star, and then we have an exoplanet that is orbiting the star. But actually, there's a gravitational influence of the planet to the star, and the star to the planet. So which means that then the system orbits around the center of gravity of these two bodies. And if you have more bodies, of course, then it's more complex, but the idea is the same. Which means that when you look at the star, the planet you don't see, you look at the star and you see how this star sometimes goes away from you and this star comes towards you. And in the same way as we always explain the Doppler effect, you know, so when an ambulance goes far, then you have a different sound, but when it comes to you, because there's a change in frequency when the object moves that is emitting the sound, or in this case, light. And therefore, so we look with very high resolution spectroscopy, so not 3 or 4 colors, but hundreds of thousands of colors. We look into the light of the star. And then we see exactly the spectrum of the star, and then this spectrum moves towards the red and towards the light, the blue. And with this movement, we can derive the mass of the exoplanet. Because then it depends, if the planet is very big, this of course will move, this movement will be much more important. If it's smaller, it will be very, very shallow, what is we want to do also with Plato. It's very challenging. But what is interesting is that this is a lower limit of the planet mass. So, because it depends on the inclination, and then with this measurement, it doesn't tell exactly the mass, but a lower limit of the planet mass. It gives you a measurement of the eccentricity. But as you see already, that because we want to do a spectroscopy that is of resolution 100,000, so 100,000 bits for color we want to see, we need a lot of photons. So then in order to do this measurement, you need bright stars again. You cannot do it with a 16 magnitude star. And this method is used by ground-based observatories. So far, I've seen some proposals to go to space, but actually there's not real benefit of going to space for this method, because most of the knowledge the knowledge that we have now, and also the problem we have basically is that the activity of the star gives a signal that is higher, for example, than the signal induced by an Earth-mass planet. And therefore, the difficulty is more disentangling the signal of the star and the planet than having a better precision from the point of view of going to space. So on the ground we can do it already, but it's quite challenging, and then it's done indeed in ground-based observatories. Okay, so what do we know until now with all these methods that I have explained? Some others that I'm not going to talk about, but most of the exoplanets that we know have been derived with these two methods. Okay, so here you have a plot of all the exoplanets where we have a knowledge of the mass, of the lower limit of the mass, and then here is the star-planet distance. This is in logarithmic scale, so that's why it's a little bit grouped everything, in order to see the farther objects, and then this is also the mass. But the important thing is that the exoplanets of the solar system, they are here in, these are the solar system planets, which is in the Jupiter, Saturn, Uranus, Neptune. Here is the Earth, Venus, and Mars, and Mercury. And well, you see already how relatively empty this part where the Earth is. And what we have seen until now is that we have discovered a lot of exoplanets that we didn't even think that they could exist until we have started this. For example, hot Jupiters. So they are giant planets orbiting closer to their stars. So they are really hot. Some of them are thousands of degrees. They are very close, and they are really as big as Jupiter. Also, the first exoplanet discovered was of this type, but you see that we have, this is actually a mixture between radial velocities and also transits, but well, you see that indeed there are a number that we have discovered of this in this range of masses and these distances. Then we also have observed planets that are bigger than Jupiter, so you see Jupiter is here, this is logarithmic, so this is 10 times bigger than Jupiter, that are relatively far from the star, so that you see here we are going to 10 times farther from the star, even 100 times, so they are really far. Other type of objects that we discovered that we don't have in our solar system is what we call super-Earths, mini-Neptunes, and ocean planets. And these are planets that are larger than the Earth in radius and in mass. And actually they have composition and structures that are completely different, and this is one of the aspects we want to study because we haven't seen it closer by, I mean, in our solar system. So that's why it's very interesting to understand these exoplanets here. So what are they, so then what are they made of? And then we can understand also much better what is the next thing, which as you see is this lonely, empty, relatively empty area that we have here. So the question again, is our solar system common? So we cannot answer this question because this area here is empty, not because there's nothing, but because we haven't got still, or we are in progress of having the instruments in order to understand how full this will be or not. Maybe we are really unique and there's very little planet, but it's an observational bias. And that's why this has to be considered when looking at this plot. And that's also the rationale for doing what we are doing, of course. Another important aspect is that we want to detect these exoplanets that we haven't seen before, but we also want to know better about them. And in order to do the first characterization, of course we would like to know everything, but the first characterization is their radius and their mass. If you have radius, then you have mass, then you can estimate the density of an exoplanet. And the density will tell you approximately if it's a gas planet, it's a giant planet which a very thick envelope of hydrogen or helium. Is it, for example, a water planet where most of the planet is an ocean, much more than on the Earth, because on the Earth is only 0.02%. So actually it's only the layer around that is covered by water, but the rest is all rock. But there are exoplanets that we think they can be even up to 50% of water, so then this is really, as you can imagine, very thick, deep into the exoplanet. Okay, or indeed it's a terrestrial planet, it's a rocky planet. There's a completely different density, so at least we can start classifying exoplanets with this knowledge. Okay, what happens, what we know now? I already explained to you what is the transit method, what is the radial velocity method, so here I plotted the 6,000, a little bit more exoplanets that we have confirmed so far, that are confirmed that are exoplanets. Here you have the brightness of the star around which they orbit. Here is the number. And the different colors indicate for which ones we know the radius, for which ones we know the mass, and for which ones we know both. So we can indeed know their densities much better. Okay, so then this blue one, here you see is a very big one, is for the planets where we know the radius. And then this mainly comes from Kepler and TESS. And indeed, there's fantastic knowledge that we gather, but as you see, they are distributed around stars that are relatively, well, fainter. So they go a little bit on the fainter side of the star distribution. Then we have here in beige the mass, well, the ones that we know the mass or a lower limit of the mass. So you see that this distribution, because we already said before that this measurement needs a lot of photons, so obviously then you see that they are distributed closer to stars that are brighter. This is the overlap. These are the exoplanets for which we know the radius and their mass. They are in red. But if you want to know much better about exoplanets that are of the size of the Earth, for example, so then let's assume 2 Earth radii, which is already quite big, but okay. Then you get only this green, this green fringe here or so, And then it's very little, it's only around 200 exoplanets for which we have the radius, we have the mass, and yeah, actually it's very interesting, but the problem is that they are all very diverse. If they were all the same, okay, 200 planets, you say, well, we have enough. But every time we see an exoplanet, they are all different. So they have different characteristics, and that's why this is just an artistic view of the different structure and compositions of the exoplanet, of the planets of the solar system. And then, well, you already see how different they are. So that we have the giant and the ice planets. Here we have the terrestrial planets, which are also completely different in structure. So, okay, we want to know much more also about exoplanets around much farther from us. And then this, just also to give you an idea how diverse they are. So here I just plotted the planets that are relatively small, because this goes to 20 Earth masses, and this is equal to 5 radii. And I plotted here the exoplanets for which have radius and mass. As you see, there are many that we don't have this. And then for which this knowledge is with a precision of 20%. So as you see, this is already quite broad. And these colors here are different models. So for example, the red one is iron, the second one is 50% iron planet, a rocky planet would be on the, indeed, well, these two. Then we have the green one, which is 50% water, and the one is water. And as you can see, then indeed you have a distribution all over the place, so that they are really completely diverse. Also the error bars don't allow you sometimes to tell exactly what the composition is. And then when we go here to the area of the Earth, then we also have an empty space. Okay, so altogether, again, this is a representation of how different they can be. So for example, giant planets can have, this is the pink, is hydrogen, helium, envelope. Then we have volatiles that can be in the form of ice, for example. They can be water, it can be, again, also liquid or metallic hydrogen or so. Then we have maybe a rocky core. Then you see the different types of composition for the ice giants. Then we have indeed these super Earths and mini Neptunes that we have seen. Maybe we have, for the same size, we can have indeed a planet that has an envelope of hydrogen and helium, or you can have a very little hydrogen and helium, and you can have volatiles, a lot of water, and you can go indeed, and when we get to smaller exoplanets, then maybe we have this kind of thin atmosphere like the one we have on Earth. So then that's why it's really completely diverse, and this is what we want to investigate, basically. This is very schematic, but it can be much more complex, and indeed the different proportions in the interiors also. Another point that we need to understand is not only the importance of the density is something we want to investigate, but also the distance from the star, because the distance from the star will tell us about the temperature of the planet, and of course it's very close to the star, the planet will be very, very warm. If it's farther from the star, it will be cold. There's an area in between that we call the habitable zone, and the habitable zone is a very simple concept. As I said, habitability is more complex than that, but we have to start somewhere. And this is the region around the star where the exoplanets orbiting there can have water on their surface. This is very important because when you talk about Jupiter, for example, and their moons, maybe we have oceans of water under the surface of the ice, and they are much farther away, the habitable zone. But we are trying to see conditions similar to Earth, so that's why we say habitable zone in this context is the area where water can exist in liquid form on the surface of the planet. And then if we look again at what we know now, so then here I represented, this is the distance of the planet to the star, and this is the mass of the star, so then here is the sun, and these are the stars much smaller than the sun, that you can see they can be 5 times smaller in mass. But we have here the solar system again, so the Earth, Venus, Mercury, and these are the exoplanets that are again small ones, so less than 2 Earth radii, for which we have the radius and mass. So from the 6,000 that we have, still there are only very few, but as you see, the habitable zone Also even for stars that are much smaller, which is easier to detect because the planet is closer, and then there are different, transit is also deeper and so on. So even in this area, so then there are not too many, and then it's quite empty. And this is what we want to do with Plato. So we want indeed to get more, discover new exoplanets, to get more information on the radius, on their mass, and on their age. I will also see afterwards, and also to fill the knowledge of the habitable zone with characterized exoplanets. Okay, so then with this aim, we will be able indeed to start addressing, because these are very complex questions, how do planets and planetary systems form and evolve? Are they potentially habitable planets? What are planets made of? What are the properties of their host stars? And then with all this, then we will be able to start understanding better, I mean, as I said, it's a longer process, if our solar system is unique and if there are other systems like ours. Okay, so I think that by now I already gave you an idea of what are the most important aspects that we need to look into if we want indeed to fill this green zone and then to learn much more. We need to observe bright stars, because otherwise, if we want to know radial mass, you know, they don't overlap, so then we really need to observe bright stars. We need to observe a large number of bright stars, because we are going to use the transit method, which is the one capable now to do this. And then, because of the orientation, again, we need to observe many, because for many of them, we will not be able to observe it. We also need to be very sensitive, because we want to detect variations of the light that are of the order of 80 parts per million. And in addition, we want to observe planets that are in the habitable zone. So it means that the period will be around 1 year. And therefore, you need to observe for long periods of at least 1, 2, 3 years. Well, normally 3 years would be the best, in order to be able to detect this exoplanet and to confirm it. So not only to detect it once is very difficult, but to confirm it. And then the approach that was used for the Plato mission was to use what we call multi-telescope approach. If you want to build a telescope that has both a wide field of view, you need really a wide field of view, and the sensitivity, is very difficult to do it for space. Very difficult, because then you are constrained by mass, you are constrained by volume, you are constrained by, well, other engineering aspects. So that's why the scientists who came with the proposal for Plato, they thought, okay, why not making a number of telescopes and make them overlap such that we can cover a large area of the sky and then still achieve the sensitivity. I will explain afterwards how this is done. And that's why, well, there was a lot of studies from 100 cameras to, I don't know, 8 cameras in order to see what the optimal configuration was. And in the end, so then it was decided to have this configuration. And well, this is what we ended up with the Plato satellite. Here is the engineering model. This is not the flight model yet, but it's a beautiful picture in the acoustic facility of ESTEC, where you see indeed the satellite. It has a mass around 2,000 kilos, 2,500, what is the limit, but now the latest measurements are a little bit lighter. And it has a size of 3 meters times 3 meters, well, you read it here, yeah, so it's quite big actually, so it is. And then when the solar arrays expand, then you have 9 meters end to end, so then it's quite a large satellite. It's going to be launched in January 2007 with Ariane 6.2, and the consumables are so far defined for 8.5 years, but it can be much more if the injection maneuver is the right one. Plato is built by a consortium of industries that is led by OHB in Germany, and then there is the main collaborators of this team is Thales Alenia Space and Beyond Gravity. Then the payload. Well, the payload of Plato is 24 what we call normal cameras, and they operate in white light. And we see the transits in white light, and with a cadence, it means every 25 seconds we take a picture. So it's quite often in comparison with other missions. Then we also have 2 cameras that are one in the red filter and one has a blue filter that operate with much faster cadence, and then this is also because they are for brighter stars. We will use them for science, for the brightest stars, but also because they are in the loop of the satellite to determine the pointing. I mean, as you see already, what we want to see is this very, very small variation of light. So every movement of the satellite on the sky causes variations of the light that may be bigger than actually this small dip that we want to detect. And therefore, we have these cameras in the loop with the other cameras that are normally used in our satellites to point the spacecraft, to make sure that this precision is much higher than it would be without them. And then this is actually very important. Here you have the CCDs. Well, the CCDs of Plato is a sort of wonder of engineering. I mean, we have 106 CCDs. We have 2 billion pixels. 2 billion pixels. They are huge CCDs altogether. They make a camera of more than 0.7 square meters, which is the largest one launched into space, and then until recently, also the largest one built for astronomy on the ground. And the cameras have been built by a consortium of universities and institutes, which is the Plato Mission Consortium, in collaboration with ESA. These are just some nice pictures. But you can see when we were building the spacecraft, here you see, well, already the payload module with the first camera installed, which we're all very happy, first camera installed. Then actually it's very nice to see this picture, because when you see the satellite, you cannot even imagine of the complexity inside. I mean, I've been working on this field for some years. I'm not an engineer, and I'm really always amazed at actually how, yeah, the work that the engineers are doing with all these interfaces. As you see, the harness is rather complex in order to make sure that in our particular case, which is even more complex than average, with 26 cameras, this is all coming to a good place. And then this is indeed also Thales with the service module, where this goes in for the instrument and satellite control. Okay, now I'm going to explain how we do this. How we manage to observe indeed bright stars, and at the same time with good sensitivity with the 24 cameras that we have at Orla. So this is the field of view of Plato. The field of view of Plato is around 2,200 square degrees. And for you to imagine that this is an area of the sky where you can fit 10,000 full moons. So if you are looking here and then you see the area of Plato, is really, really huge. So 10,000 moons fit here. And in the way that the cameras are organized, they are mounted in 4 sets of 6 cameras each. And they are slightly misaligned. So they are not all pointing to the same place, but some are pointing to a larger area, and then so 6 cameras are overlapping in the large area around here. Then 12 cameras, these areas with a little bit lighter blue, 18 cameras in this area, and 24 in the center. This is where all of them overlap. Obviously, you don't get the same signal-to-noise ratio when you are pointing here than when you are pointing with 6 cameras, so we are overlapping with 24 and adding their signals. But in this area, then you will be able to observe fainter stars with the same signal-to-noise ratio as here for brighter stars. And when you add everything together and then you do an estimate of what is the number of planets that we will be detecting, then it's already a good number in order to justify building this mission, having this overlap with covering the area like this. So if other missions, if you only have one telescope, so then this is much smaller, of course. And then you have, if it's smaller, you can observe less bright stars, and then you end up indeed observing a distribution of stars that is speaking more to the fainter side, which is not very good. Okay, the orbit of Plato, or the Plato will go to the second Lagrangian point, and this is the Sun here. Here you have the Earth. This is the orbit of the Moon, and then the second Lagrangian point is 1.5 million kilometers from the Earth in this direction. And the satellite will be orbiting in it's quite a large orbit around this point, and there are also other satellites. Also Gaia is there, JWST is also there, James Webb. We also have had Planck, for example, and Herschel. So that this is now a very common place to take your satellite when you really need to be very stable, to not to be worried about the stray light from the Earth or the Moon, so not to have eclipses constantly. So that when you really want to see very stable and follow the light of a star for 2 or 3 years, the very stable conditions, the best thing, of course, is to go farther from the Earth. And this is what we go to the Lagrangian point. And one of the characteristics of Plato is that actually, while it's moving around the L2, it's also moving around the Sun, and the solar arrays have to be pointing always towards the Sun, because otherwise we don't have power, and you don't want the Sun also going into the telescopes, especially because we want to, again, have stability, and we don't want to be worried about this other light that is not of the stars that we are observing. Okay, in order to do this, the satellite rotates every 3 months. This is unfortunately not ideal, but you want to have this stability that we talked about. So that's why the requirements for this rotation are very stringent. That actually in the way that it's rotated, in the way that it's pointing, such that the star actually falls again, not in the same pixel or the same CCD, because everything has rotated, but at the same distance from the optical axis point of view. So that in order to reduce these perturbations. So, okay, so this is the way that it's going to operate, but of course then we have this 3-month maneuvering that will have an impact on our light curves, and then we have to take into account. Just to complete this, I just wanted to add another scientific topic that I haven't mentioned before. Well, when I showed you the formula, then you said it was that you learn with the transit method the radius of the exoplanet with respect to the radius of the star. And therefore you need to know very well the radius of the star if you want to know very well the radius of the exoplanet. The same applies to the mass when you do the radial velocity method. So the only way that you know very accurately the radius and mass and other properties also of the planet like the age is if you know very well the star. And that's why what we do with Plato, we use another technique which is called astereosismology. And this is a very complex technique, but it gives really amazing results. And this is based on the fact that the stars oscillate, our sun oscillates, and they oscillate because when there are perturbations, there are sound waves. It's a little bit like earthquakes. It's similar to what you see with an earthquake. There are sound waves that propagate in the star, and then they bounce. They also penetrate different layers of the star, depending on the density, of course. When they become in resonance, then actually you see that each star, depending on the mass, on the radius, on the age, on the structure, has different peaks where you see these resonant frequencies. So actually you take the same light curve that we are observing, then you look into frequency, so then how often this variation happens, and then you can derive from that the structure of the star, the radius, the mass, and the age, much more precisely than with any other method. And this gives us a lot of information because, the universe is not static, our planets are not static, everything, well, as you can imagine how different the Earth was when it was formed, than what we see now. I mean, there was, of course, no biosphere, probably it was a lot of lava, there was a completely different type of exoplanet than it is now. And therefore, it's not only that you need to know how the exoplanet radius mass density is now, but if you know the age precisely, and then you have many observations, then indeed you can derive evolution. You can derive evolution of how, in the same way as we do with stars. So we have snapshots, and then we can understand the evolution of stars. So we do the same for planets and for planetary systems. And so in the way that we are doing Plato, this I already explained. In space, then we do the transit method. I already explained that we get these parameters. Then we use astereosismology, so we can derive the precise stellar radius, mass, and age. Then we also have inside the mission, which is a little bit different from other projects, the follow-up with ground-based observatories of the main stars in our sample. And this is done with the radial velocity method that I explained before to determine the minimum planet mass. But then, of course, since you know the inclination here, you know the radius here, so then with inclination you can derive here the real mass. So in total, in the end, you see a very good characterized planet. You have a good characterization in terms of orbit parameters, planet radius, planet mass, and age. And this is the basic philosophy of Plato. For the ground-based observatories, we are going to go to, well, mostly now to the south, as I will explain. These are just a few of the observatories that we are going to use for confirming the exoplanet and also to measure the mass of the exoplanets on the ground. And as you see already, the European facilities that are of most interest to us are in Chile, and this is indeed the ESA, European Southern Observatory telescopes, that have in particular 4 telescopes of more than 8 meters. And in one of them, the best spectrograph for the derivation of the mass is installed, which is called espresso. And that's why when we look at the Plato observation strategy, so there are a lot of constraints to observe for more than 2 years a field, and we also have scientific constraints to optimize the content of this field. So we have 2 possible candidates for the long duration pointings of more than 2 years. One is in the northern hemisphere, this is the galaxy, this is the galactic plane, and one on the south. Here you can see the Kepler field, as you see, is smaller, much smaller than the Plato field. These are all observations that have been done with other satellites. So we want in this field to have in 2 pointings and also observing more than 245,000 stars that are less than magnitude 13. And also we want, especially when they are dwarf and subgiants, because they have to be indeed the stellar stars that are similar to the Sun. We have a sample for stars that are smaller than the Sun, which are magnitude 16. And then we have the brightest stars, which will be around 15,000 in 2 pointings, with a noise-to-signal ratio random noise of less than 50 parts per million in 1 hour, which gives us the best precision for the finding and determination of characteristics of Earth-like planets. And then we call there's something that we call the prime sample, for which we are going to derive the ground-based observations in order to determine the mass. And then this is just a view on the sky of the Plato field. So this is what is going to be observed. The first pointing on the south, the reason being that indeed so far we don't have spectrograms on the northern hemisphere that can do the same work as espresso instrument can do for the determination of mass planets, or Earth mass planets, sorry. But then that's why we are going to the south. We are going to observe with espresso instrument and other ones, where we have, of course, all the other planets that are a little bit bigger. And yeah, there's some overlap with observatories that are not so much north for the lab for this third. So there'll still be possible to do some observations in northern observatories. Here just the distance of the stars that we will be observing, because as many times I get the question, so how far are they? For the brightest stars, so then this is in parsecs, so you have to multiply by 3, so around 600 light years is where we are going to have the stars that are more similar to the Sun, but you see that there's a distribution, of course, but just to get an idea. And for the ones that are fainter, so we are going to something like 1,500 light years farther away. So yes, in this range, these are the distances that we are going to study with Plato. Well, the planetary yield. This depends a lot on the models that you have and how you estimate the population. So I have here just put I will not to look at each number in particular, but just to get a feeling, okay? So what we are talking about, because there are different models and so on. For the planets that are relatively close to the stars, so you see for periods that are less than 100 days or but then for this we have a pretty good idea of the statistics. So all these numbers of planets that are here for Jupiters, Neptunes, super-Earths, Earths and super-Earths, that you see there can be from hundreds to thousands. So all these are estimates that we are going to thing that we are going to observe with Plato. When you go here after this part, we actually don't know. Because until now, we really haven't been able to derive the percentage of stars that have Earth-like planets in terms of distance and in terms of radius. There are completely different estimates. Some people say 1% or less than 1%. Others say 50%. Some models give 100%. All of them should have it. But that's what we don't know. For this particular calculation, the estimate is between, well, around 6-28%, so then you can vary a little bit there. But we are estimating this, but it could be 4 times, or it can be much less. So, but it's also an interesting finding, because we really find that the percentage is much smaller than 20%. We are a little bit special, I mean, compared to what we see. If it's 100%, so then it would be a different story. So that's why, just to give you an idea, in the habitable zone of sunlight stars for Earth-sized planets, we are talking about tens of planets that we expect to discover. There will be thousands of many other types and distances, but of these characteristics, only of the tens. And then, okay, this is just a little bit the same. So then, for the longer period planets, that you have here the points, a simulation of for the stellar radius. So this is one. This is the Sun, and then this is a little bit smaller, and the habitable zone. And these are the ones that we expect with simulations to see with them. Well, just to give you an idea of what we will be observing, so that this every quarter we have the rotation of the spacecraft, and then measure the light. This is what we will see per camera. You see what the rotation of the spacecraft causes. Indeed, there are jumps. These jumps are of the order of 1 to 100% of the light. But then we will take all these, we will make it, well, flatter it, we will remove these jumps, we will combine the light of all the cameras, and this is more or less what we will obtain when we will flatten it completely out. And this going already to a factor of 10, so then this is already a factor of 10. But then, if we want to see, these are the tranches that we have injected in the simulation. If we want to see an Earth-like planet of long periods, that is orbiting around 1 year, with a 3.3 year simulation. So then you will get this light curve, that this is what we expect to observe. So the nominal duration of Plato is 4 years, but we expect indeed that we will be able to observe more, because the consumables are there, and it all will depend on the extensions that we get from our responsible committees. And then, okay, so this is just to indicate that how the data will go into Plato. It will go into an archive with all the community, everybody can have access to. And we have an open call that really starts very soon, the 7th of April, an announcement of opportunity for anybody who wants to observe with Plato objects that are not in our list. Then they can apply to that. Well, so here is just to complete. We have what I showed you before. So now we expect Plato to be launched next year. We have indeed Area, that is another ESA mission that will be looking into the atmosphere compositions of exoplanets, but it will not look into the atmosphere compositions of Earth-like planets, because for this we need the next generation observatories. And we also will have the Roman Space Observatory launched by NASA. And this one will detect a lot of exoplanets that may be similar to us, but in a technique that you cannot do the follow-ups. You cannot learn so much about the properties, but it will be very useful for statistical purposes. And just to finish, so then, okay, just nice pictures of where we are, what are we doing in ESTEC. Well, this is actually interesting, because Plato came by boat to ESTEC, so that it was, most of it was built at OHB, close to Munich. And then the Mannheim was, you see here is the container where the satellite was, and then we are just, they are just putting it on the boat that went through the Rhine and came here to Katwijk. And Katwijk, so well, okay, so then it was unloaded, and then it was wrapped. So these are the engineers at the ESTEC Test Center, unwrapping the satellite and indeed putting it in the right position after the trip through the Rhine. This is already when the solar panels were installed. These are folded, because the satellite will be launched with the folded panels, and then they will unfold when they are in space. So just in the test center, you can see the cover. Actually, the cameras are many times covered to avoid contamination. And then, so here, let's see if I will show you. Yeah. So then this is a little bit just an idea of when we did the test for the opening of the solar arrays, so just to get an impression. And actually the chamber is not big enough to have both opening at the same time. So we had indeed to open one and then the other, and this is the test that was carried out then. Okay, so then for the next, this is another one of the test that we are doing is the vibration test. So let's see if, so basically this is indeed to simulate the conditions of the launcher. So the satellite will go into the launcher, the vibration will be quite strong. And then we have tests that are lasting 1 minute each, in which we go from 5 to 100 oscillations per second. So it goes, this is very, so this at the beginning you see indeed how the satellite is standing these oscillations. In the end you don't see them anymore because the oscillations are so fast that you don't see by eye. But it's also interesting to see sometimes they go in resonance. And of course this is what you want to know. I mean, because when the vibration of the satellite reaches resonance for whatever element or for the whole spacecraft, these are the critical ones, because of course it's when it amplifies the oscillations and the vibration. And then, yeah, this is, the test was successful, so far it looks very good. And what is happening now, the satellite is in the large space simulator. The large space simulator is, as its name indicates, simulates the condition of space in terms of thermal and vacuum. So it goes to 1 million times less pressure than the one we have. And actually we also have a thermal environment that simulates in space, so going indeed from very cold of minus 80 degrees so to warmer like 160 degrees or so. And then here you have Plato without the cover of the cameras, and I found it quite beautiful to see also the reflection actually on the lenses. And even in the fast camera, these are the two fast cameras that I mentioned for the bright stars that have different filters. And you see indeed actually the different colors. So it's quite nice to see. And normally you don't have this view because of course then you really need the normally covered in order to avoid contamination, and then you don't have this perspective. So yeah, this the large space simulator is 15 meters high, and Plato is a little bit more than 3, so you can imagine the scales here. And then just the last one, so then I'm just going to show you, this is of course a simulation, because this is what we expect to see very soon in the beginning of 27. This is assuming that Plato has already gone out of the Ariane launcher, so then it has been already independently flying in space, and then how you start with the thrusters, controlling the altitude. This is when the solar arrays will open in space. Then you will, again, so the thrust is just controlling the altitude of the spacecraft, in the right orbit. And you see here the antenna. This is the high gain antenna that will communicate to Earth, also deploying. Plato goes far to the second Lagrangian point. And again, so once it's in this orbit, then it starts rotating every 3 months, 90 degrees, in order to keep the solar arrays and the lights and away from the and okay, and this is it. So, and then, well, okay, so I hope that I can convince you that we are living in exceptional times for the discovery of new worlds. I mean, after Plato, there will be other missions and other observatories that are going to do wonderful science, and I wanted to thank you for your attention. Thank you very much.
Thank you so much for the interesting talk. Thank you so much, Ron, for your is it like for the James Webb, the opening of the solar panels, or what is the most critical one on this mission?
Well, clearly opening, well, as you see, the mechanisms are always critical. We have very few mechanisms in Plato, but yeah, obviously they are critical. So we need the solar panels open, we need the high-gain antenna, because we have other antennas that are obviously for commanding and in case some problems appear that are covering 360 degrees, so it doesn't matter where the satellite is, you can control it. But this is the antenna for the science. So then this one has to indeed decouple very well. And then the next step is that both the pointing is stable, so as we have specified in the requirements, which seems to be the case with the tests that we are doing, but in orbit it may be different. And the other thing is indeed the very, very complex commanding that we have. For 26 cameras, we have, as I said, 10 billion pixels. For most of the stars, we are going to reduce the data on board. So for more than 100,000 stars, we are going to reduce the data on board. So then this software has to work very well. For the brightest stars, we are downloading an area of the star around in order to get more information and be able to do the data reduction much better. So then these are the critical, so then the commanding, and in the end, well, we have a noise budget. I mean, the noise budget assumes certain behaviors, and they are based, of course, on the best knowledge that you can acquire on the ground from the testing, from the calibration, etc. But again, when you are in orbit, so then I don't know, there's almost every satellite sometimes see that water condenses. Other satellites see that there's more some increase of micrometeorals. I don't know, there are always sometimes things that they are solved eventually, but indeed, it's difficult to tell exactly what to expect, but at least the ones I told you are then critical.
Thank you.
I was wondering, it was going quite fast a bit about astroseismology. I was wondering if you can tell a little bit more about the techniques that are used to look at that.
Yeah. So, okay, astroseismology the good thing is that with the same observation that we do with the exoplanets, you can do astroseismology. The requirements are mainly on the cadence, so that's why it's very important the difference between Plato, for example, and Kepler. So there are two things, the brightness of the stars, as usual, the brighter the star, the better you can estimate all the variations, and also that you need a certain number of observations, because, for example, the sun, a star like the sun, oscillates or has the main oscillation mode every 5 minutes or 5 minutes. So if you have an observation that you take an image every 5 minutes, then you don't see anything. So you really have to observe with a refinement that allows you indeed to have this observation with the cadence that is enough in order to be able to see these variations in the light. But of course, when you look at the light curve, then you don't know, you see just variations. So the best thing and what astroseismologists do is to look into the frequency space. Okay, so if some have some mathematical background, Fourier transform, for example, and then you see exactly, so in which frequencies. So then you see what the plot I shows. So actually you see these peaks, And then these peaks, when you have, there are some peaks that we already know from the astroseismology on the sun, and by the way, this is where it started, helioseismology. So we can connect models with the observation of these peaks. And then you can start indeed simulating, okay, for this star with this size, with these layers of, I don't know, the hydrogen burning, for example, helium burning, all these kind of things. So you can make a structure, a mass, and so on, and then you apply models, and then these models you can compare with the peaks that you see in your observation. And then, well, in some cases, even only with the separation of the modes, you can already have a pretty good idea of radius and mass, for example. But if you want to know the age, you have to go much more detailed modeling. And then this one, indeed, is by comparing the models that we have with these peaks that you see, all these peaks. But it also means that these are challenges for the modelers, of course. So that's why for Plato, since now we are going to get data that is unseen, is unprecedented, the modelers need to also refine what they are doing and the observations, the assumptions they are making. And we even have, sort of competition between groups of modelers that we gave them, okay, if you have this input, just tell us what is the characteristics of the star, and then just see how close they get to each other, if there are discrepancies and so on, because it's a challenge for the observers and for the modelers to be able to model with good accuracy in order to get explanation about this. Otherwise, is this enough? Sorry that...
No, it's
yeah.
Should I choose or do you want to choose?
Yeah, no, please do it yourself, because you see who said first.
Okay, you in the back.
How do you know what elements the planets are made of?
Yeah, so then, well, we can have, if you have a density, so as a first approximation, I mean, when we, it was a little bit fast, but you have, for example, imagine that Jupiter, no? So Jupiter is mostly, we have hydrogen gas envelope and so on, and we have, then you have a density because you have the mass with the radial velocity measurement, with the radius you get the volume, because we assume, well, just imagine very simple. Mass, you have volume, and then you divide mass per volume, and then you get the density. So for planets that have gas, this density would be smaller than if the planet is made of iron, for example. This is in general terms, so then that's why, at least in general terms, you can say what is the dominant element on this planet. If you want to do much more careful analysis, then indeed, again, it's the same as with asteroseismology. You have to model how the dependence of the radius and the mass goes, like in this, in the models that there are models that show you, okay, if the planet is made of water, so this is the dependency of radius and mass that you will see. If the planet has a lot of silicate, this is another dependence. So that's why then, again, adjusting the models with the radius and mass values that you can get relatively close to the composition. We estimate that with 5% of the accuracy in radius, that what Plato will be doing for planets like the Earth, we will be able to distinguish relatively well also some interior structure. But for super Earths, for example, we have what we call degeneracies. So actually for the same point in radius mass, you may have different structures inside. And then for these ones, well, we will keep the degeneracy, because we can say, okay, there's probably a lot of water, or there's probably... but then the best thing to break this degeneracy is to investigate atmospheres. And the atmospheres is for in vitro missions to do it, or for future observatories when they come. So then that's why when we have the measurement of the atmosphere, it will be much easier, but it's not simple, because for Jupiter and Saturn, as you know, I mean, we are going there, and we are having measurements in situ, and still, the people who are doing modeling of their interiors are discussing exactly what is inside Jupiter, and what is inside Saturn, and what is... So even if you have a lot of data, it depends how much you want to know. But that's why you have to start somewhere, and the first one is indeed gaseous versus water versus terrestrial.
For example, the cameras are all white light instruments.
Yes.
And the amount of overlap the different cameras have, and things like that. So how are those decisions made? Can you give me an example of the kind of decisions?
Yeah, for white light it's relatively simple, because what we want to do is to observe stars like the sun. And then, well, the sun, the maximum number of photons is invisible, so then this was, this was not so much discussion about this. But for the cameras, this is much, much more complex. I mean, when I started in Plato, I look, as I said, I mean, the engineers basically and the scientists all together were looking into all the possible combinations of cameras and numbers of cameras to optimize the number of stars you can see, the signal-to-noise ratio that we'll achieve, and also the probability of detection of exoplanets. So that's why this is not one plot. I mean, this is indeed an analysis that you have to simulate, knowing the population in the galaxy, because you know, of course, another point very difficult. Close to the galactic plane, you have a lot of stars. Farther, you have much less. So where do you point? Of course, you want to observe many stars. But if you go very close to the galactic plane, all the stars are together, and then everything is blended, and you cannot separate them. So then if you go to the far from the galactic plane, and then it means that you are in an area with less stars, and then there are too little. So that's why all this, so then you have to optimize considering the population of stars in the galaxy. Indeed, also not only the number of cameras, but also how big each camera is. So then that's why it's a complex trade-off.
So just one small follow-up question. Are all these decisions based on hard data, hard science, etc., or through personalities, etc., or people
Or
evaluation?
JWs,
Is it all based on hard data like signal-to-noise ratio and simulations, etc., or there are some other things that play a role like the organization and the people in the organization?
well, I mean, all our missions have constraints in terms of resources. So then, of course, I mean, we never do, but scientists, we always want more, and then we want to, actually, Plato started with 34 cameras, actually, so then we started with 34 cameras, now we have 26. And then the rationale is always that indeed you need to be able to build it, so from the engineering point of view, you have to be able to do it, then you have to be able to pay for it, and you have to be able to put it in a launcher, because of course, I mean, if you go to bigger size of the spacecraft, then you need a larger launcher that is more expensive. So then indeed, that's why, I mean, the process from having an idea of what we want to do and then how you want to build a spacecraft to actually the final one that is being implemented, as you see here, it takes, I think that probably 20 years since the people started thinking about it. And of course, then you go and then you propose your mission, and then it's not approved, and then you have to go back. And then it's studied, and maybe you are 3 years in study, and then it's not approved again, and then you have to come back. So then it's quite tough, and then very difficult process, and it takes years, because indeed you want to optimize, considering indeed not only, as you say, the science part, but the programmatics.
Yeah, you mentioned the guest observer program. I was just curious how that would work. Like, if we were always looking at the same view of the sky, like how would people request like specific observations? Is it like follow-up of stars that are in the field of view?
For the ground base, you mean, or for in general, or for the guest observer?
Yeah, I guess in general, like how does the guest observer program work?
Yeah, so what we are going to start is with the area of the sky on the southern hemisphere that I shown. So then we are going to be there, well, at least for 2 years. I think that in the end probably will be 3 or even more. That's a little bit how the spacecraft works. If it's, as I said, the accuracies are what we are estimating. But then, okay, so then we will be observing more than 150,000 stars simultaneously. So then this is the idea, so there's a large number of stars. Then we will be distributing the data to the public, most of this data, a few months after it has been produced. And for people who want to observe different objects than the ones that we have put in our catalog, or with a different capability, we have a guest observer program that only covers 8% of the telemetry, but okay, there's an opportunity there for people to submit their proposals and to use the capability of Plato, for example, I don't know, to observe planets around white dwarfs, for example. This is something that we are not having in our core program, because we are looking at some stars, but I'm sure there will be people proposing to look at planets around white dwarfs. Okay, this is indeed for observations in orbit. And then once the data comes to the ground, there are 2 options. So for 20%, so for 20,000, I should say, of the stars into fields of view, we are committing to deliver the observations on the ground also. So the consortium is organizing this observation and talking to all the ground-based observatories in order to be able to access them and submit proposals and so on. So if people want to join, you can join the consortium, or anybody can join the consortium to already be involved in this effort. And otherwise, this is only for this, in the southern hemisphere, it will be 15,000, in total it will be around 20,000 stars. And for all the other ones where there are exoplanets, then it will be up to the community to organize themselves. Probably the consortium will do something to help the community, and maybe to also together with the community coordinate ground-based observation programs for the rest. But again, when the data is open, so anybody can do the ground-based observation. So people have to apply to ESA, or if one has a, well, actually, even with amateur observatories, you can do the Jupiter-like planets, or we can do the larger planets. You can follow up even with relatively small telescopes from the ground. And if you want to do the velocities, there are other instruments that are telescopes of around 2-4 meters that will do very well for the larger exoplanets, not the Earth mass, but yeah, there's mini Neptunes, Jupiters, etc.
One last question.
So there are systems where you have a star with a very large scale and strong magnetic field, and if you have a planet orbiting relatively close in, you could have something like an interaction like you have with Jupiter and Io, where there's material coming from the atmosphere flowing along the magnetic field lines onto the host star. And last year there was a publication using test data that found that one of the host stars was flaring with the same sort of like period of an exoplanet. So I was wondering whether something like this could also be useful for Plato.
Well, actually, this, if this, well, it will be great for this kind of things, because you will get very precise, more precise light curves than in TESS. Again, it depends on the magnitude of the star, of course, but for the same magnitude, you get better precision than in TESS. You get also longer timelines, because in TESS, if you are on top, then you can have a long one, otherwise it's shorter. So actually, with Plato, as we said, with all these more than 100,000 stars that we will be observing simultaneously, and that most of the data will be available relatively quickly to the community when we sort out the pipelines. Yeah, exactly, this will be used for that, because the data will be even better than the one that you have until now. Yeah.
Thank you.
That's all the time for questions we have. Please join me in thanking the speakers.
Thank you so much.
And